Ya, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azamudin Majid, metric number AE 2038, and today I would like to present about the design for the single line diagram. So this is the single line diagram that I already performed by using the ETAP software. So this is the net feeder. The rating is about 30 kV, and the short circuit rating is 100 MVA short circuit. And then it will connect to the utility bus, and then from the utility bus it will connect to the cable. So the cable rating is about 1 kV 3 core cable, XLPE. The frequency is 50 Hz, and then the diameter is 35 mm square. Okay, next we go to the transformer 1. So the rating is 6.25 MVA, and the rating is step down from the 30 kV to 11 kV. Okay, next we go to the switchgear A. Switchgear A consists of the transformer 2, induction motor M1, induction motor 2, and the pump. So all of this rating is according to the instruction. And then it will from the switchgear 2, it will connect to the transformer X2 and connect to the LV bus 1. From the LV bus 1, it consists of the induction motor 3, lamp load 2, and the lamp sub. Okay, next I will perform the load flow analysis. First, we click for the load flow, and then run the simulation at the right button corner. Okay, so this is the initial percentage of the voltage for the downward feeder. For the utility bus, the percentage voltage is 100%, which is the nominal voltage. Next, we'll go to the switchgear A. So the voltage rating is 98.48%. And then for the LV bus 1, the voltage percentage is 37.78. So the value for the voltage percentage for the LV bus 1 is lower compared to the switchgear A. This is because when the load is when the bus is further away from the network feeder, the percentage of the voltage will decrease because of the loading, such as the induction motor 2, pump hose, pump, and induction motor 3. Next, we will go to the report manager. Just click to this one, and then we go for the bus result, so that we can identify the power factor and current for each bus. So we click the nominal kV, and then click for the ampere loading. Okay, so as you can see that this is for the bus, for the each bus. Just add the sub bus, and then for the LV bus 1, the voltage is 97.78 and the ampere loading is 96.49. Okay, next we go to the bus result. So in this bar result, we can identify, we can monitor the ampere rating and the power factor. So we just click the power factor, and then click for the rating. So this is the ampere for each branch, and this is the power factor for each branch.
Hi, my name is Mishahira binti Rahmat. My metric number is AE 200019, and I will present for the installation of synchronous generator. And this is the connection of the network with the synchronous generator. And this is the generator. The generator was set at 1 megawatt, 6.6 kilovolt, 80% of power factor and 90% of efficiency. And the S of the synchronous generator is 1.25 megavolt per ampere, and the generator was connected to a transformer to step up the voltage from 6.6 kilovolt to 11 kilovolt. to connect with the SWGRA bus. So when we do the load flow analysis, and we obtain this value, and we can see that for each branch, the current flow is lower than the current flow before installing the synchronous generator, and the power flow for each branch also lower before installing the synchronous generator, and the power factor for each branch remain the same and maybe only have a slight change. And for each bus, the voltage level is higher compared to the voltage level before installing the synchronous generator. So that's all for the synchronous generator.
My name is Nur Natasha Amira binti Manasir and my metric number is AE200041. So, for this presentation, I will present about the power factor corrector. So, this is the power factor corrector connection. The connection of the capacitor is based on 11 kV, 200 kV per bank. The operating load is 596.3. So since the value of capacitor bank is 200 kV per bank, so we need 3 capacitor bank to make it value to 600 kV. So it can support the load. Installation of a power factor corrector has been made rated at 11 kV, 200 kV per bank at the switchgear A bus, and the network connection is as shown in the figure. For the installation, a capacitor has been added to the network connection to monitor the current flow, power factor, and voltage levels. So, based on the table in the Excel, it has shown current flow after apply the power factor corrector. Based on the current flow shown, the current value is lower compared to the values of current flow after installing the synchronous generator. The value of power flow for cable 1 and transformer 1 is lower after installing the power factor corrector, but the value for transformer 2 and transformer 4 is increasing a little bit, and the value for transformer 3 remains the same. Next, for the power factor value after installing it has shown that some of the values are constant and most of the values are increasing at the load. This voltage level percentage for the power factor corrector is higher compared to the value after installing a synchronous generator.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nur Hakim bin Ahmad Osman, number matric AE200042, and I will proceed with the installation of PV array. So, the question asks to install a PV array at the low voltage bus bar. So, we will focus at the low voltage bus bar only. As instructed, the question asks to use sub manufacturer and the model number NE80EJEA, and we need to decide the number of solar panel in series and parallel as we calculate the rated power, the total demand from the low bus, which is the bus that the low voltage bus, which we want to install the PV. Demand at total 757 kilowatt, and then we decide to use this configuration: 24 solar panel in series and 32 solar panel in parallel, that will produce 61 kilowatt in total of 400 volt. And we need to set the inverter rating. Inverter rating will rated at 65 kilowatt at 500 volt, which is safer with from which can handle the output of the PV array. So now we will do the load flow analysis. As you can see, the PV array producing 54.5 kilowatt to the load, and the grid also providing 6 kilowatt to the low voltage bus. As we do the load flow analyzer, we can see the total kilowatt and the power factor. As you can see, the induction motor 3 that on the low voltage bus had total amount of 23 kilowatt and 88% of power factor. Then that's all. Thank you.
And I will explain for the task G for the short circuit analysis. Firstly, there is a continuous system from the installing the PV array. And firstly, we need to do is we change the short circuit analysis to the short circuit mode. That we click on to the edit study case and it show the system shows this. And we need to click on to the all buses and fault under the bus selection. But before that, we need to check on the standard that we use into the system. So we use the IEC standard into the system. After that, what we need to do is we need to run line to ground, line to line, line to ground, and three-phase fault into the system to initiate the short circuit analysis. So the value shows that the short circuit analysis at the alternating bus, SWGRA, LV bus, pump, bus, and transformer. So next we need to do is we need to do short circuit plot by click on the IEC 61363 to generate all the phase current. So from here we need to choose only 3 different bus, which is LV bus 8, SWGRA 7, and alternative bus 7. And then we select on all the phase current to the system. So from here we can see that there is a 5 different graph, which is total fault current, AC component of fault current, DC component of fault current, percent DC component of fault current, and top envelope fault current. This legend show the indicator that we use, which is LV bus, SWGRA, and alternating bus. So lastly, what we need to do into our system is we need to click on the report manager. So we click on to the complete version of the PDF. So from here, we can see that there is a total number of buses is 6, 5 total number of branches, and 6 total number of machine. So from here, what we want to see is the short circuit summary report. So at here, there is a bus of 3-phase fault, line to ground, line to line fault, and line to line to ground. So we need to see for the LV bus 8, at the line to ground is 6.047 kiloamps, line to line fault is 5.049, and at the line to line to ground is 6.081. So from here, we can say that at the line to ground fault current is the larger of the 2 faulted line current. So at the report also shows the sequence impedance for the LV bus, SWGRA, and alternative bus. So at the positive sequence, the LV bus shows the value of 0.04135. At the negative sequence, show the 0.04276.
And at the zero sequence, show the 0.03712. That's all from me. Thank you.
Yeah, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Sulaiman bin Qasim. My matrix number is 8E20018. Today I will present about our assignment. I will present for the question H, which is harmonic analysis. For this question asks to find the THD at 3 bus, which is LV bus 1, SWGRA, and utility bus. We move on to our simulation. This is our circuit. Okay, this is our circuit here. And for the 3 bus, which is utility bus, SWGR A and LV bus 1, I already add the filter for harmonic. Every filter I already keyed in the value here. And move on to our power grid. Power grid already changed the library for the harmonic. We use type current source, manufacturer the typical IEEE, and the model 12 plus 1. And same goes to all transformer. Just we just pick the same type of the harmonic here. And generator and this load. Okay, after that we just go harmonic this part, and we don't forget to change this part for the plot graph. We just make what we want to plot at the bus, and we just make sure the LV bus 1, SWGRA, and utility bus has this mark. After that we just run the simulation, and this value for our harmonic for this current. After that we can plot the graph. We just tick all the bus and we click the tab of graph. And this is our graph for the harmonic for this circuit. That's all for me. Thank you.